Welcome back. We are in tutorial track 1, the second session of the morning, which I'm ecstatic to say is OFI Libfabric APIs for MPI and CCL. Let me introduce our speakers. We have 3, all from Intel, colleagues of mine. First, we have Rajalaxmi. Angadi is a seasoned engineering manager and leader with over 19 years of experience in the software industry. She excels in the productization of OFI Libfabric and the management of cluster infrastructure for HPC and AI. Her career encompasses roles in leadership, architecture, software development, and performance engineering. She's made a significant contribution to industry standards such as Open Fabrics Alliance, Ultra Ethernet Consortium, NVMe, and DMTF-SNIA, demonstrating her dedication to technology innovation and advancement of cutting-edge technologies. She also co-chairs the Technical Women at Intel Network, fostering the development of women in technology. Second, we have Juee Himalbhai Desai, who's a middleware development engineer at Intel Corporation to support Libfabric software productization. She has 4 years of industry experience working in computer networking and has been with Intel developing and testing Libfabric components for the past 3 years. Prior to Intel, she was with Pluribus Networks working on physical layer technologies. And last but not least, we have Peinan Zhang, who is a senior software developer at Intel with over 20 years of experience in developing performance tools and runtime libraries. Her current focus is on high-performance computing networking solutions and performance analysis technologies, providing OFI and profiling tools to assist developers in building robust and scalable HPC and AI applications. Peinan obtained her PhD in computer science from Purdue University. So with that, please take it away. And just another quick reminder, please post your questions in Slack and I will handle them as they come in. Thank you, and please take it away.
Thank you so much, Dave, for all the kind introduction. There were really good line of talks this time. And I would like to thank the coordinators and organizers of HOTI for bringing us this wonderful conference. Interconnects are hot, and HOTI is helping make us aware of those. With the advancement in AI and the scale at which the systems are growing, interconnects become very important. And the libraries that are enabling these interconnects even become more important. This is Rajalaxmi, along with Juee and Peinan. Would like to present a tutorial on Libfabric. Next. So today we will be looking into a brief recap of what Libfabric is. In the past tutorial presentations at Hot Interconnects conference, we have talked about Libfabric APIs, and we have also talked about how a traditional client-server applications can be mapped into the Libfabric kind of application. This time we are interested in talking about how do you build it, how do you install, how do you set them up, what are the various knobs and environment settings that you can make use of when you have different type of fabrics there. We will also see some simple MPI examples and an example with collectives as well. We have developed profiling hook into Libfabric, and we will see how we can profile at the Libfabric level as well. This profiling hook will help us debug or understand if there are any performance implications. So with that, let's dive in. Next. Okay. Today we will be with the AI infrastructure. With the huge computational requirement that AI is posing, we need hundreds or thousands of compute elements. In this diagram, you can see that there are various servers that are stacked in a rack, and they are connected in a complex network. So all these servers, they cannot function as a standalone system. They will have to be connected to form a cluster or a supercomputer that is capable of solving complex scientific and AI problems. So when we have these multiple servers or compute elements needing to be connected, they have to be connected in various ways. with various fabrics at various layers. Like you can see there, we have a rack of servers in one rack, and then which are connected by a switch. And then when we bring multiple racks, then we'll have to make a different type of connections with the leaf switch and spine switch there. As we scale to the large number of nodes, we have to use this hierarchy of switches forming a network. And we can see there are like leaf switches that are connecting into the racks, and then there is a spine switch which is making a total connection there. There are different ways to make efficient topologies. We're not talking about those, but we see that there are different type of fabrics there. We can see that for inter-node connectivity, we can use fabrics like Ethernet, InfiniBand, Fiber Channel. And for intra-node connectivity, now we can use PCIe and GPU links like Intel's Xe-Link or NVIDIA's NVLink. With the increase in the number of GPUs and the capabilities of each of these GPUs, we now have switches at the link level as well. We have NVLink from NVIDIA connecting these GPU links. So different requirements of network catering to various new entropies may result in different topologies that we have. So hardware and its features are going to keep evolving. And with all of this complexity, we need to have an efficient software that enables all of this. Next. So Libfabric is the library that is helping in addressing this complex variety of fabrics hardware there. OFI and Libfabric are used interchangeably. It is a communication library providing common APIs for HPC and AI applications or middlewares on the top. And at the bottom, it provides abstraction to the diverse network fabrics. And we already saw in the previous slide that we have a large variety of fabrics to deal with. Libfabric maps the applications to these fabrics through the various providers that it has. The goal is to optimize the path to the hardware and provide a scalable communication that makes middleware and application developers' lives easy. Imagine if a developer has to program for all of this set of hardware. And it is not only the fabrics that is changing, but we also have compute elements that are changing, going from a simple CPU to GPU to DPU, IPU, and you name it. So Libfabric is trying to help bridge these evolving changes at both ends, at the application end and at the lower hardware end as well. Today we are with Libfabric, we are at 1.22.0 version, and we are marching towards 2.0 by the end of this year with many enhancements, and it is supported on different operating systems as well. Next. This is a zoomed in image of Libfabric, but it's an abstracted view. It's not really showing like the exact layering or all exact components of Libfabric, but it is a good abstracted view to help us understand things. Let us see from bottom. At the bottom, we have different fabrics hardware along with its kernel counterparts. So we also have different type of compute elements, like I mentioned, like CPU, IPU, like we have DSA engine there, and we have like now computational storage and things like that. So at the bottom, it's evolving at that faster pace with all of these new fabrics and compute elements. Let us shift our focus on the top now. And the top layer, which shows middleware applications and libraries, and we can see that the focus is trending towards the AI. And the collectives are becoming more important. And we have listened to many talks in this conference about talking about those. Imagine if a middleware developer have to program for each of these fabrics and the variety of compute elements that are at the bottom. It would be so inefficient, and there will be so much of duplication, and the maintenance will be an overhead. And like each of these fabrics also have their own set of features. And if the application or middleware developers have to tweak to those features, then again, it's an added overhead. So it will complicate things when we try to incorporate all of these things. So this is where Libfabric is helping. It provides those common API interface to the middlewares, and underneath it maps to various fabrics through the providers that it has. It makes it efficient by optimizing the path, um, uh, by reducing memory footprint, or by providing scalability features. It caters to all class of developers, going from naive to experts who can make use of appropriate knobs within Libfabric based on their requirements to make the best use of the fabric features underneath. So with Libfabric today, we have a hooking provider to use GPU memory, like HMM hook, supporting CUDA and Intel GPUs. Also, there is NIC to XPU coordination, which includes XPU initiated communication, NIC initiated communication, etc. And there is also a peer provider that helps with seamless scale up and scale out, where there is one endpoint to the application, while underneath two providers are communicating based on what is the need, like whether if it is a scale up or scale out, a particular provider can can take care of the task. So we also have offloading of collectives implemented. With all these cool features, Libfabric is helping deal with the evolving fabrics, and now it has become a part of UVC stack as well. Next. Let me shed some light on UVC. UVC is Ultra Ethernet Consortium, and it uses Libfabric as its northbound API. The goal of the UVC is to optimize HPC and AI workloads. And UVC wants to modernize Rocky. And it is accomplishing all of this by lowering the latencies and enabling higher network bandwidth utilization. So it has various cool features like packet spraying, which enables like a flow to simultaneously use all the paths to the destination. And when we pair this one with the scalable endpoints that Libfabric is providing, it may provide additional benefits there. Then there is flexible ordering with the Libfabric API. This avoids the requirement of like reordering all the buffers, which will help in reducing the cost, latency, and the complexity. There is congestion handling, there is telemetry with packet trimming, and in-network collective offloads, etc. There are a lot of cool features. I think Uri also talked about UVC in this conference, I think yesterday. So in this diagram on the right, it shows that Libfabric is sandwiched between UVT, which is Ultra Ethernet Transport, and the application. UVC is also preserving the existing AI frameworks and HPC library APIs, which means that you don't have to really change anything on the top. It just integrates with the Libfabric as its common communication library. So, yes, I think Libfabric is making good progress there. So there is a lot of development that is happening on this one. Next. So if we zoom into the Libfabric layer, again, I'll be talking, I'll just talk briefly about this. This is again the same diagram, but like a zoomed in view of the Libfabric layer. We have two sublayers within Libfabric there. The top one is like, talking with the application middlewares, exposing APIs to them. And in the bottom, the gray bar there is showing like one of the fabrics which has transmit queues and receive queues in there. It is connecting to the provider layer of Libfabric at the bottom. So there are different set of APIs that Libfabric presents. The control APIs, which is the first block there, it is helping us with operations like discovery, like if I get info, that will help us get to know what are the available fabrics underneath, what are its specific features, what I can use. And then there is communication APIs. These are basically used for all sort of connection management, like basically setting up a connection, tearing it down, managing the address vectors, like basically mapping the endpoint to the fabric address and things like that. Then we have completion APIs. For each of the send and receives that we do through the send and receive queues, we also have completion notifications. Those are being notified with the completion events with the event queues and counters. So all the management of that part is done in the completion set of APIs. Then we have the data transfer APIs, which are crucial for sending and receiving the data itself. The purple block, towards the lower layer, lower sublayer of Libfabric, it is providing the similar set of APIs, but at the provider level. When I say provider, it is kind of linked tightly with the particular fabric. So let us see how the APIs flow from the application to the Libfabric and into the provider. Next. So I think in the previous slide, we saw that top we have like MPI, and then we have MPI CCL. We have a shared memory provider. Sorry, shared memory SHMEM, and we have Libfabric layer, and then there is a particular fabric at the bottom, and its provider. So when we do MPI, we will not go into all of the APIs, and this is not exact program flow, but this will give you an idea about how the APIs are mapped between these layers. We kept talking about exposing the APIs to the application middlewares, and then we have the corresponding APIs at the bottom. We will see which ones are those and how do they map. So when what MPI init does is it initializes processes for communication. It sets up all the data structures, and it exchanges information that are necessary for communication. And then there is an MPI communicator that's established. Then at the OFI layer, what it is trying to do is it's trying to make that communication path efficient. Actually, it's trying to make it lightweight. And we can see that when MPI init happens, there is a corresponding OFI component in it. We have taken from OpenMPI, so we use that as an example here. And when with OFI component in it, we have FI get info, which is a control set of API, like we talked in the previous slide. It gives us details about what are the fabrics. It returns a list of providers based on the hints that are given to it. And if we wanted Libfabric supported collectives, then the hint capabilities, if we set it to FI collectives, it will help us know if a particular fabric, if a particular provider supports collectives or not, whether it is supporting collective offloads or not. FI endpoint creates an endpoint. It exchanges addresses, and it binds the memory regions, completion queues, counters, and address vectors to that endpoint object. Then there is FI get name. It will get our endpoint names and publish sockets to KVS. For collectives, which are nothing but multicast atomic operations, for address vector setup, there is a AV set. I have marked those APIs with star there for collectives especially. And this AV set is a list of desired addresses that we want to use for collectives like all reduce. And this AV set points to a multicast address, which means that it will, when that multicast, anything that is happening on that multicast address, it will be spread to all of those endpoints or like addresses which are part of that. The join collective occurs on the universe of this address vector. It basically creates a multicast group. And there are two ways to do two ways to do join collectives. One is OFI managed, wherein the provider implements the coordination in band, and the provider will talk to all the peers and sets up the communication groups and reserves the resources. And the second way is the application managed join for the collectives, wherein the application establishes an out of band connection, and if the resources are already reserved there. So at the provider layer, we can see the corresponding provider layer calls. Like for example, an FI endpoint will, we have a corresponding verbs open endpoint there. And then for the collectives, we have a collective provider in the Libfabric, and we can see that COLL underscore create underscore op API over there, which is at the collector, which is at the provider level. So yeah, for like FI connect or like FI open, it will ultimately resolve into RDMA connect or RDMA resolve route and RDMA create endpoint and things like that. So this is the very like high level view of flow of like how if anybody wants to understand like what's happening there and how Libfabric is getting used and what APIs are getting called, and this is basically showcasing that. Later we will see a simple example, and we'll see how it actually goes through a particular fabric, and we can also see the demonstration of the actual use of that fabric as well. Next. And now we will see what happens in MPI send. We can see the flow here going from the MPI send going into FI send, which will result into FI inject. In a lightweight call, what it does is it converts the MPI rank to address, and it initializes the tag, and then it injects. In a normal mode, it creates the request, handles the data type processing, and sends it via FI context there. There are advanced MPI send operations which may use a scalable communication, scalable communicators basically. So the scalable endpoints can be used when a separation of resources required or when parallelism is required. So it's basically what the application or the developer wants. It can be tweaked accordingly. It basically achieves parallelism through attributes like ordering, and it exploits makes best use of the hardware resources there. When we come to the collectives part here, we have like corresponding FI reduce, which will trickle down. It actually kind of goes back and forth between that collective provider with the collective schedule send and collective schedule receive, or collective EP all reduce type of calls there. And for the just MPI send, I think we can see at the bottom, it kind of resulted into an IBV post send there. So this is the general, we have in the interest of time, we just took like 2 APIs and then just briefed about those. With this, let's dive into the demo and see how we can build and install Libfabric. What are the knobs that we can set, and see an execution of a program. Over to you, Juee.
Okay. Thank you, Rajalaxmi. So I'm going to demonstrate how we can build Libfabric and install it. And then we'll also see how we can build OpenMPI and then install it with Libfabric and run a few demonstration examples. So let's see how we can install Libfabric on our local system. We'll go over 2 ways here. There are multiple packages available, as you can see in this image. So there is a Libfabric package that is only Libfabric specific source code. And then there is a fab test package, which is a fab test is a test suite for Libfabric. So one can test Libfabric APIs using fab test. So if anybody wants to install these two packages separately, they can do that. And then you can see the source code as well. This is the complete package along with Libfabric APIs and fab tests. So the location of this package is in GitHub in our OFI Libfabric repository. Now there is another way of cloning Libfabric using git clone. So for my demonstration, I'm going to use the git clone method here. Now let's see how we can build Libfabric. So the first step here is to run our autogen.sh script. That script will invoke all the GNU auto tools and it will set up our environment to start building Libfabric. After we run the script, we can do the configure and then give some options here. So the first option is prefix. This is the directory or the path where you want to install your Libfabric. So we can give that with -- prefix. Next is -- with Valgrind. So if Valgrind is available on your system, it will enable Valgrind annotations. And the most important here is what providers we want to enable or disable in our build. So we have two options here, -- enable provider and disable provider. And then as you can see, there are multiple options with enabling a provider. So when you don't give any option, that is automatically enabled. So auto is that option where you don't say enable provider, it will automatically enable it. Yes is a specific. So if you want to enable a provider specifically, then you have to say yes. And if you don't want to build a specific provider, then you say no. And that is also similar to how the disabled provider works. Next is the DL option. So this will build a provider as a dynamically loadable library. So if you have any provider that you would like to use during runtime, then you can build it as a DLL. And the last option is directory. So this is saying that if you have any provider available locally on your system, then you can give the path to that provider here, and it will build with that in the installation that you have in that path. Now let's go over a few examples of how we can build it. So the first one is the default option where you just give the prefix where you want to install, and we don't give any of the enable or disable provider options. So this will enable all the providers by default. Next option is, let's say if you want to disable verbs. So here we say that we give the prefix and then we say disable verbs. So this is going to disable verbs and install Libfabric in our home Libfabric path. And this will only disable verbs. It will enable all the other providers by default. Next example is if you want to enable debug code paths, and if you want to also use a DLL provider. So let's say we want to use TCP as a dynamic loadable provider. So we give that option here, enable TCP's DL as a DL. And then if you want to also enable debug code paths in the Libfabric APIs, then you can say -- enable debug. So this will install Libfabric in the home Libfabric path, and it will enable all the providers. Just it will enable TCP as a DLL. Okay, so now since we have built and installed Libfabric, how do we make sure that it is working, or how do we make sure that we downloaded the correct version? So there is a utility called FI Info. It will be available once you install Libfabric in the bin folder. You can find this utility. So if you run FI Info test with, let's say, --PTCP here, TCP is the provider that we want to test here. So it will give out all the available TCP fabrics within your system or within your node. And that is how you can make sure that we have installed Libfabric successfully. And let's see how we can see the version. So FI info dash dash version will tell you which version exactly did you install. So it also gives you FI info, the Libfabric .so version, and also the API versions. So we'll see how this works out in our example. Next, I want to show how we can build OpenMPI using Libfabric. So it is quite similar to how we build Libfabric. We have to run the configure with first string prefix. So this is where you want to install your OpenMPI. Next is disable OSHMEM. So OpenSHMEM is disabled in Libfabric, in OpenMPI because we do not want OpenMPI with Libfabric for our examples, and this is enabled by default, so we have to disable it specifically. Next is dash dash with Libfabric. So this is the path where you had installed Libfabric, and it is a library that you would like OpenMPI to build with. So for our demonstration part, we installed Libfabric in the home slash Libfabric path. So we could give that path over here. Next is dash dash with Slurm. So this will build OpenMPI with Slurm, and if during runtime anybody wants to enable Slurm OpenMPI jobs, then this would help with that. And dash dash enable MPI 1 compatibility. So this says that there are different MPI specifications like MPI 1.0, 2.0, 3.0, and so on. So this says that we want to enable the MPI 1.0 specification or the symbols that are available in MPI 1.0 specification. You can also, depending on what your application is, you can also give other specifications as well. So an example of how this would work is, let's say in the prefix, we want to install our OpenMPI in home slash OpenMPI, and we disable OSHMEM. And with Libfabric is the home slash Libfabric as we installed earlier in this directory. We are giving that with Slurm and enable MPI1 compatibility. So I will go over a demonstration for this one. Okay. So let's go to the demo folder, and we are going to do git clone of Libfabric. Okay, so let's see how did that work. So we have Libfabric here now, and let's see if we have any installations of Libfabric before we try to run this. So I'm just going to see FI info dash vtcp. So as you can see, we don't have this command installed because we don't have Libfabric installed yet. So let's go into Libfabric and run the autogen script. Okay. Now, since we have this, we'll just build it by default. That is the default option. So we'll just say we want to build Libfabric in our home slash demo path. So this will build all the providers by default. And we can also see later on, it will provide a log of what providers it built. So here you can see that it built all of these providers that are available with Libfabric. And the last step would be to install it with make-install. So if anybody wants to have a fab test installation as well, that will come after this. So you have to go in the fab test directory and then follow the same steps. So runty./autogen.sh script, and then configure your prefix with the path of this Libfabric installation. So as we can see, our Libfabric is built in demo/Libfabric path. Now I want to show. Okay, so we are here. So let's see. Let's see this. So we have bin, include, lib, and share folders that were created when we built Libfabric. So now let's check if it was built successfully. If we go to the bin, here we have our FI info utility. Let's run that with TCP. Okay. So as we can see, all of these TCP fabrics popped up. So it means that we have these many fabrics available on this node. And let's also quickly check the version. So it is the 1.22 version that we installed. And then this is because we just cloned it from upstream. So upstream has this version. That's why we see that this is the version that we want, and it is working fine. Okay. So let's see how we can install OpenMPI along with Libfabric. So I already have the tar file here. I will just untar it. Okay, let's go into the OpenMPI and configure. So the prefix that we want is our home directory and OpenMPI demo. After this, we want to say -- with slurm and -- with the Libfabric. This will be the one that we just installed. And then MPI1 compatibility. So we'll get all the MPI 1.0 specifications. And let's say we want to disable OSHMEM. Okay, so this is now running. This takes some while, so I'll just pause this. I have another installation on another node here. So I'm just going to demonstrate my MPI based send receive example first. So let's go back to the presentation. So let's see how the environment variables, what kind of environment variables we have to set to run our examples or to enable OpenMPI to use OFI Libfabric providers. So I have two OpenMPI and one CCL here. So these and TCP and verbs are the providers that we'll like to show here. So for TCP provider, the first most important environment variable is the FI provider. Whichever provider that you would like to use, you have to set the FI provider to that one. So for TCP, it will be TCP, and for verbs, it has to be verbs provider. Next is a FI TCP interface. So whichever interface your application wants to use, for let's say we want to use the ETH1 or ETH2 interface for our application, then you can set the interface with this one. Similarly, for verbs, we have FI verbs interface. So this can be IB0, or it can be Mellanox, or it can be any other verb-based interface that you would like to use. Now we have three MCA based, these are open MPI based environment variables. So the first one is MC dash dash MCA PMLCM. So to use OpenMPI, we have to set this, which is setting the point-to-point messaging layer to CM. So CM is an engine that supports matching network layers, and it uses matching transport layer components or MTL components. The second one is dash dash MCA OFI. So we set this because OFI is an MTL component. And the third is dash dash MCA MTL OFI provider include TCP. So this will tell the application that we want to use the OFI TCP provider. Similarly, we can see on the verb side, these two will remain the same, but for the verbs part, we have to say that we want to use the verbs provider. So we give verbs as an argument to the MTL OFI provider include. So these are the basic OpenMPI environment variables that we set to run basic applications. Now let's go to the 1CCL part. For the 1CCL part, the FI provider remains the same. That is the important one. We have to set it to TCP for TCP provider and verbs for verbs provider. And similarly with FI TCP interface and verbs interface. So these can be set for any collective library. And for 1CCL specifically, we have the CCL ATL transport set to OFI. So for OpenMPI, we can see that we use three different environment variables to set the transport to OFI. With 1CCL, we have CCL ATL transport to OFI. So this will set the transport to OFI. And since we already mentioned that we want to use TCP provider with FI provider environment variable, it will use that. And for verbs part, it will use verbs if we mention this. Now, there are also some SHMEM based environment variables for 1CCL, which will also have the same set of environment variables. You have to say FI provider SHMEM and then FI SHMEM interface. So whichever interface is available for your system, you can mention that, and then the transport is set to OFI. Okay, so let's see our MPI example using Libfabric. This is a very basic send receive based example. So we are going to use MPI send and MPI receive calls. What we are trying to do here is send an integer message between two ranks. So let's see how this is going. So first we set the MPI init. This will initialize our MPI environment. Then we get the world size and world rank. So world size is all the processors available on your system. And then we will assign ranks to each of those processors. And we are only going to use two processors. So if we find anything more, then we just abort it. Next, we are setting the integer number to 10. So this is the message that we want to send. So if we are zero rank, we use MPI send. We are sending an MPI integer type of data type. So we set that here. And then if we are rank 1, we are receiving. So we are using MPI receive API here. And the receive data type is also set to MPI integer. Now we finalize that and then we run the example. So what we are trying to do here is we'll set the provider to TCP and interface to ETH2. And this is the command that we'll use to run our example. So we'll show how we can increment or like send the message, and then we'll see how the counters, the transmit and receive packet counters on ETH2 interface works. So let's switch back. This is the example that I have here, MPI send receive, and I'm just going to run that. So before that, we will see our ETH2 counters. Okay, and then let's set the provider to TCP and interface to ETH2. and then we just run the example. Okay, so we use MPI run to spawn the application. We are using two hosts, N1 and N2. So both the hosts will have one process each. Then we are setting the PMLCM, MTL to OFI, and then the OFI provider include TCP. And then we give our executable of our application. So it says process 1 receive number 10 from process 0. This is what we expected. Let's check the counters again. Okay, so as we can see, the transmit and receive packets have increased a little bit. We just sent a small message, so there is a small increment in the packets. So I have a few logs that shows how this all worked and what went underneath. So let's go over the logs. Okay, so first things first, the N1 cluster or the N1 node is finding the component OFI component, and it will load the OFI component. So these are the OpenMPI based calls that happens, and it will select the OFI component. Once it selects the OFI component, we see the Libfabric work here. We wanted TCP provider, so we are going to enable TCP provider. And then we also said that we want ETH2 interface, so that is also taken into account here. It goes ahead and opens a fabric of 192.168.20.0. So this is the fabric on our system that we wanted to use because we mentioned ETH2. ETH2 has this IP address, so that is why it opened the fabric associated with that IP address. Now, this fabric has a lot of capabilities that it can support, like FI message, read, write, send, receive. But we are only interested in send and receive, so we are going to use those capabilities here. Then it says it initializes the address vector. So since there are only two processes and two addresses, it initializes it to size 2. On the second node, we also see that OFI component has been selected. And then this entire part is where it will add the address of both the nodes. So we can see 20.1 is node 1, 20.2 is node 2, and it adds the addresses of both the nodes in address vector. And then we see that it connects to the node 1 connects to node 2. And then once it is connected, we see the FI connected event here. And then after the connection happens, we see the message transfer and then close down the connection. So this is how MPI send and receive calls follow into the Libfabric calls. And after our connection and everything is done here, we just unload the OFI component from both nodes. So this was a basic example using MPI send and receive. Now I would like to show a collective based example that is a MPI all reduce example. So let's see how we do that. MPI init is the first thing that we do. So we just set all the our environment, MPI environment variables. Then we get the world size, associate a rank to each of the processors. And then what we're trying to do here is create a random array of elements. And then each process will have a random array of a number of elements. So first thing is they will create a local sum of all the numbers, like each process will have its own local sum. And then we use MPI all reduce to calculate the global sum, and all the processes will get that global sum using MPI all reduce. So that is the program that we have written here. And then we finalize the MPI environment and we'll run the example. So here as well, I would like to use TCP provider and also set the ETH2 interface. And my commands are almost same to what we had earlier. So MPI run. We are going to use 4 hosts for our example. So each host will have one process. So one process per node. And then all the MCA based environment variables. And then this is our executable. And this number is the actual random amount of random numbers that each array will have. So let's run with 50. So each process will have an array of 50 elements, and it will create a local sum of those 50 elements. Okay, so let's go and run that. So again, I'm going to set the provider to TCP. And then let's run the example. Let's run it with 50 elements, and then we have 4 rows here for 4 processes and 1 process per node. Okay, so first we see that there are local sums for each process, and then all of the process receive a global sum. So 107 is the total of all of these numbers. So this is our example, and let's see how Libfabric worked underneath this example. So similar to what we saw earlier, the first thing will be OFI component initialization and selection. So all of the nodes that we wanted to use have that. So it does that. So we can see here that component OFI was selected for all of the nodes. Then we see that we wanted to use the TCP provider, so it took that in account. And then it opened the fabric that was associated with the ETH2 interface, which is 192.168.20.0. So, and then we also see that it registered the TCP provider. And then this fabric has all these capabilities available to it. But again, we are trying to just use the FI send and receive here, because we send and receive our global sum between all the processes. So this time the address vector size is 4, because we wanted 4 processes. And here we can see that we get FI connected event for each of the nodes or each of the process, and address is getting registered into the address vector for each of them. So 20.1, 20.2 here. This side there is 20.3 and 20.4. So all of the 4 nodes were registered and connected. And then we see that our global sum is received by all of them. So this is the basic implementation of a collective and using Libfabric with collectives. Now, after this process is done, we just remove the address vector. We remove the addresses from the address vector, and then we close down our OFI component or unload it. So I also have another example that shows how collectives work with Libfabric, which is like Libfabric based collectives. So let's go ahead and see that. So in the Fab test suite, we have a test called FI multi-node collectives. That test will run all the collectives available inside within Libfabric, and it will trickle down to the Libfabric based collectives. So let's try and run that. Okay, so I have a script here that runs the FI multi-node collective example. We have used 2 nodes here, and then we want 4, like 2 nodes and 2 process per node kind of setup. So we can see here that it starts 2 process on each node. So here we ran the join test, FI join collective. So as Rajalaxmi mentioned, FI join collective will collect all the available nodes or addresses into the FIAV set attribute structure. So that is a basic test that shows, okay, it works like that. Then we have the barrier test, barrier collective test. Then we have the all reduce test that we ran. So this also shows that we are using the FI collective APIs, and then we see that it is it is going to the collective endpoint all reduce call and following collective do all reduce call. So this is how we saw these type of calls in previous slides. So it shows that it follows these APIs or these calls. So let's see here. This is the test, and we just saw that we ran all of these tests. So in the interest of time, we are not going to go into much detail here, but please feel free to reach out to any of us for more details on this. So I'm going to, we'll see now next how profiling works with Libfabric. So I'm handing it over to you, Peinan.
Can you release the share? Okay.
Yeah.
Have you seen my share?
Not yet, Peinan. No. Yeah, it is coming. Yeah, we
Okay.
can see.
Yeah. Thank you, Juee. I'm going to introduce the profiling capability in Libfabric. Profiling has been added to Libfabric to help debug and understand the low-level communication characteristics. It helps to understand how communication API being used in the communication application middleware, help understand the performance difference in using different network interface, using different communication protocol. It also can help to gain insight into a provider's implementation to understand the limits or optimize resource utilization. Profiling provides aggregate statistic in Libfabric. Compared with tracing, profiling has much lower overhead. What features are available in the profiling in Libfabric? We have two parts. One is a profile hook. It is for understanding a communication API are used in application middleware. The second part is profiling interface. It is for profile provider, including the profiling API and the profile support in providers. The diagram here in the right-hand side showing this component, where this component sit in the Libfabric. Profile hook is intersect Libfabric API. Well, the profiling API actually is part of Libfabric external interface. The profile support in the provider is part of provider's implementation. I'll go to each component for describe each component. First, let's look at the profile hook here. It intends to help understand how the communication API being used by application middleware. It is a hooking provider built using the Libfabric hooking mechanism. It hooks send receive calls, completion calls, and memory region registration calls. It aggregates the API calls and the amount of data being operated. As a result, it will show all the API being used in the application execution and histogram of the data site the being operated. So this screenshot shows the profile data from Peinan, where it use TCP provider with text message. The first column shows the send and receive and completion API being used in this example. The second column shows the message size bucket have a message size bucket, and the rest of the column shows the API calls, the distribution of an API calls in each of a bucket in terms of a number of calls, counts, and the total amount of such call, and the percentage count and the percentage amount of a data. So this will give you some idea how the application use the communication API. In this particular example, we can see like for the small size data where less than 64 bytes, it will be used inline injection, use like FIT inject. And for most like send message sent, it's around like 75% will fall into these three buckets from 64 byte to 4K byte. We have a main page FI hook. They have a session talk about the profile hook. We will describe more in this column, the meaning in more detail. Let's move to the Fabric profiling interface. It is interface extension to the Libfabric external API. It intends to provide a better debugging or profiling capability for providers. It includes two parts. One is the provider need to export some internal information. So provider decided that what information it want to share. For example, like resource usage, configuration setting, or even some like a runtime state. And application can use the API to discover what information is available and access this information. So this Fabric providing interface, including three major components. The first is the variables. Variable determine what information are available. So provider determine and export variables as a shared information. The second component is the events. Events indicate when the variable or the information is available and when the information got changed. So provider defined event and use event to inform, indicate the variable's changes. So to access the variable, application middleware can use this API. A set API can be used to discover all the variables and events and can register the register callback for the event notification and can access the variable. Variable is defined and owned by the provider, so application middleware only have read access for the variable. Here is the object type, new like a data type defined for supporting profile object in the APIs. So profile is defined as an object, same like other objects in the Libfabric. It is defined with FID and a set of ops can apply to this object. Here, the set of operation including read vars and read events. this will return a list of variables and events. Each variable and event is described as the FI profile description type, including a unique ID, data type and data size, name and descriptions. So each event and variables will be referred by this ID. Once we have this event or variable, we can use this operation read var to query event by event, query variable by variable ID, or register callback by event ID. If we want to read multiple variables, we can use the star read ops and read ops as a log to ensure like all the variable read between star reads and reads will come from the same snapshot. So the right-hand side is showing the object relationship and the APIs. We can use FI profile open to create a profile object associated with a domain or endpoint. After we have this profile object, we can use these API like query variable, query event, read a U64 data, with a callback, star read, and read. These APIs is built on top of, is a wrapper function built on top of these ops. We have a main page FI profile to describe all the data type and API in more detail. So here, the variables and event are defined by the provider. So provider need to decide it, what is like a critical or meaningful in terms of helping debug and providing in the provider. So here I show some examples. Like we have a provider added to TCP, profile added to TCP provider. The profile on TCP provider intends to help debugging the performance degradation caused by unexpected message. Unexpected message can occur in like tag matching messaging, which match the source send operation to the destination receive operation. When the text message come in and there is no post receive request matching the tag, so this message will become unexpected message. The communication layer must buffer this message until the application is ready to receive it. If there are many like unexpected message occur in workload, this message will potentially cause memory pressure, buffering overhead, or increase latency, even cause deadlocks. So TCP added this profile to allow application to inform application once such a situation happens. In this profile on the TCP, it defines two profile variables. One is unexpected message count. Another is unexpected message entry buffer. So one message arrives and does not match any like post receive request, the message will be added to the entry buffer and the message count will be increased. Once a new post receive request issued from application, the provider will check the entry buffer first. If there is matched message found, so the message will be removed from the buffer passed to the application and will decrease this count. Provider also define two events, like unexpected message received or an unexpected message matched to indicate these two situations. Here is a code snap showing the variable table define these variables. Later, I will use an example to show how application can use the providing API to query the variable value. We also have a profile in the verbs provider. Here, we focus on resource usage and the function execution time. Verbs provider to support a profile with the following variables. The memory allocated. So here, the memory allocated is the memory allocated in Libfabric for verbs provider. Not include any like system memory or application memory. And we have variable for trace the queue pair create a connection establish, and variable to calculate the connection established time and RDMA verbs call time. And in here, all the variables in the verbs are aggregate statistics. So we don't have, and it do not define any event. Application can query this variable when needed. And by the end, these variables value will be logged in the trace log. I will show, have an example to show what is the profile data in the verbs look like later. To build or to enable the profile in Libfabric, we need to build with config option --enable profile. By default, the profile is not enabled in Libfabric, so there's no performance impact. Once we enable the profile in the Libfabric, we can link this library to any desired application. There is no change need on the application side. To run, we have several environment variable need to set for provider hook provider, profile hook provider. We need to set FI hook to equal to profile. This is only necessary for profile hook. For using API profile on providers, we don't need this setting. All the profile data will be in the trace log, so we need to set log level equal to trace. I'll demonstrate how to use the providing API and show what is the profile data look like in different case. Here is a simple example to show how to use providing API. This example is RDMA tag message. So the sending tag message and receiving side is just receive the message. Post receive the message. Both send and receive will init fabric go to sequence similar like showing in the right hand side box. Let's forget about this enable prof for now. So it get info, create a profile, create a fabric, create a domain, create a CQ, create an endpoint, and allocate all the necessary resource and enable the endpoint. Once both sides enable the endpoint, establish connection, the sender can here will send in text message with the tag A0 to A9. While the receiving side will post the 3 receive requests. with tag B0, B2, and then post the 10 receive request for the tag A0 to A9. So if the sender message come to receiver side, and receiver is already finished all 13 post the receive request, everything will be fine because there is already have the post the receiver waiting for this tag message. But if the message come to receiver side much earlier than the receiver side finish all the post, the unexpected message will happen. This application want to get notified when such situation happen. We added enable profile after in the init fabric function. We added enable profile after endpoint create and before endpoint enabled. So we attach a profile object to the endpoint. Here is the code snip for this enable prof function. We want to query unexpected message count when this happens. So the first we'll call the FI profile open on a target object. So this target object here is the endpoint FID, and we can get a profile object back. After we got a profile object back, we use query variables API to get a number of variables count and a list of variables. We do the same thing for the event, and we can check with the desire or what we want the variable and the event are available. If yes, we can register a callback to the to this event. Here, we register a single callback like a read count to the event unexpected message received and unexpected message matched. This is simple. The callback is very simple, straightforward. It's read once they got notified for this event. It's just the read unexpected message count. So after read successful, this callback simply print out, oh, I got an event with event ID and unexpected message count is such value. So I will use the demo to see how this works. So I create two terminal here, left-hand within two machines, OFI 1 and OFI 2. The left-hand side, it's like showing us the sender. So I run this RDM tag message from the OFI 1, the sender's machine, use the TCP protocol. Here, I can see after I do the query variables, the query event, I got like 8 variables available. In total, there's 2 events available. And here, the sender waiting for receiver to establish the connection. So for the receiver side, I run same program with the receiver host and use the TCP. With the sender try to connect to this sender on this machine and using TCP protocol. Here we can see after a connection established, the sender in the left-hand side is sending pin message, and the receiving side is starting posting the post request. So it's a little bit slow. So after they only post to A0, the the incoming message arrived, and so it is only one tag message with waiting for A0. So we see there is I got the event 0. The event 0 here showing the unexpected message received. So the unexpected message count will be increased up to 9. And then the receiver side is post received for tag A0, A1. And each time they post one new post received, the provider will generate a new event. Here is event 1, that is the unexpected message matched. So the unexpected count will reduce up to 0. So this is just a simple demonstration to see how application can use API to get notified by the variable change. Now I will show I don't need that window. I will show how what is the profiling data looks like in the for profiling of verbs provider. The profile data will be in the trace log. So I added I set log level to trace. I'm using the same example Juee showing before. Here, instead of using TCP provider, I use the verbs provider. So I set MPL OFI provider included to verbs and specify FI provider to verbs and added the verbs interface. Here I use the manual Rocky 0 and I run the 4 process on 2 nodes, 2 rank per node. And using the same like MPI reduced executable with the 50 random number. So here here is the output for the MPI all reduced 4 process showing the local sum and global sum. Here is the follow the trace log for the profile data on the verbs. Here is the memory allocated per rank. And here are the queue pairs create per rank, connection established, the number of requests issued by this rank, and the number of connections received by this rank. We have like a passive connection established time and active connection established time with like a min max average. So these all aggregated result. And the next session is the function execution time, or list some of critical function used for verbs to establish the connection. So you can see the min, max, and average time. Here is output per rank, aggregate result per rank. So we have a 4 rank, so have a 4 session here. Okay. Next, I will show a simple example to see how the profile hook looks like. We need to set FI hook equal to profile and export still the FI log equal to trace. And then I use the same MPI reduce example. And here I use the TCP provider instead of verbs. I run the one rank per node. So this is the trace log result. The first column here is the transfer API, including the send API, receive API, and the completion API being used. And here is the message fetch bucket in this workload, and the distribution in terms of counts, amount, not percentage count and percentage amount for each like a bucket, size bucket. Yeah. Here I end up my demonstration. I'd hand over back to Rajalaxmi for giving a summary for the tutorial.
Thank you, Peinan.
Yeah, Raj,
thank you, Juee and Peinan, for wonderful demonstration there. This slide shows, just to summarize, today we have seen a high level of where Libfabric sits. We kind of briefed over the architecture, and we went into to see the APIs going from the application space into the middleware library, into the Libfabric layer, and into the provider space. And we saw a few demos showing how we can, with the log levels, how we can make sure that these are the paths that it is taking. We also saw like how we could profile and get more details if we want to debug or assess the performance of any of these APIs or elements within Libfabric. This slide gives you links for all the places, like where you can find details about Libfabric, the GitHub project. There is a GitHub link for the Libfabric tutorial example that we are trying to put all the examples that we have done in this year's tutorial, and also the previous years as well. We will, what is not there over there is a write-up of steps of how do you set up these like profiling hook, and how do you enable these things. That also we will eventually put it over there. But yes, feel free to reach out to any of us, or we have a great team of developers who can be reached out to as well. There is a OFI working group and they meet regularly to discuss different features of Libfabric and the enhancements that are happening over there. Feel free to join there. And since this is open source, you can also contribute. So yes, I think we are open for questions. We saw a lot of question and answer that was happening on the Slack, and I guess some of the questions are already answered, but yes, we can take more any other questions if there are. I think there.
Yes, thank you very much, team. Excellent coverage of Libfabric. We did have great discussion in the chat, and I highly encourage you all to read it. And I might even summarize it because I think it's a really interesting message, and my thanks to Alexia for fielding those questions in the chat so thoroughly. But yeah, as more questions come in, I'll just say that Niaz asked if you have two groups of processes and each are using two different providers, can you communicate between those two groups? And the answer is yes, but it has to be done manually with an additional endpoint. It's not automatic.
Yes.
So that led to another really interesting question, which is what's the advantage of Libfabric? I thought that was kind of it, the multi-provider support. And where Libfabric really excels is in portability. Performance portability obviously is a very complicated problem, and I think that's what Libfabric is taking on. And so the hypothetical question of like, if you're only sticking to one particular API and for some reason you will never need portability, do you have a need for Libfabric? And perhaps not, but I can say as a user, it tackles that portability problem. I work in OpenSHMEM, and sometimes I lose track of all the networks we support because of Libfabric. So
It's good, right?
it's kind of amazing. Yeah.
Yeah.
It's not to say there aren't complications. I mean, it's sort of combinatorial overload with all the different settings and options. But yeah, from my point of view, it takes an impossible problem and makes it tractable.
Mhm.
So I don't see any other questions.
There is one question on profiling, so that
Great. Yes,
Mhm.
profiling related. Is the memory alloc data included? Is the memory alloc data include the memory registered by RDMA?
No, it's
No.
when they all the memory allocated by Libfabric.
So internal memory, not necessarily what's registered.
Mhm.
But presumably the user must know how much memory is registered because they're registering it. So is that the reason the profiler doesn't report that?
No, that is the application level profiling, right? We try to profiling what is in the provider. Yeah. So Libfabric try to support that provider, allocate those memory to make it working.
That makes sense.
Yeah.
Thank you.
Yeah.
I have another question at the back of my mind. There's been a lot of talk of UEC and new Libfabric APIs, which are very interesting. And I'm curious, it's been labeled as a Libfabric 2.0, right? And I'm curious if there's a high level plan there you can overview, and if Libfabric 2.0 will be backwards compatible with 1.x, or if that's to be determined.
Yeah, there is yes. With regards to, I think you asked multiple things. One is like if there is backward compatible, yes, that's being worked on. And then if you want to know what all features or enhancements that are part of 2.0 that are provided to UEC, I think it's a kind of a big list, or like not really big list, but there are multiple discussions happening on that front. I encourage you to attend the OFI week meetings, and more team members are also participating in different working groups at UEC to drive those things. We have software working group, Libfabric mapping group at USC, which is taking care of different aspects of the mapping APIs. And then there is accelerator spec. I think they are working on some things on the accelerator. I don't know if I can talk about all of those things when they are not yet out there, but yes, different work. I can in general say that different working groups are like tackling different parts of where the Libfabric connection happens there. Yeah.
Excellent. Yeah, it's exciting developments.
Yeah.
Okay. Any other questions? We're a couple minutes over, but we're heading into lunch now. So thank you for attending. The first couple sessions, we have 2 more sessions in track 1 this afternoon, one on test and repair of interconnects, which I'm very excited for. And then finally, a rather interesting looking distributed AI tool. So please stay tuned. We'll see you an hour from now in the afternoon session. And if you have more questions, feel free to post them in the Slack channel. Those will remain. And yes, we've learned we have some excellent help from Libfabric developers in tackling your questions.
Yes, I would also like to thank Alexia for helping out with her questions while we were like busy in the presentation. Thank you so much, Alexia. Yeah, thank you.
Yes, indeed. Thanks, and we'll see you soon.
Thank you.